Right, sorry about that. Okay, so welcome to this 11th session where we are going to be talking about some of the variants of generative adversarial networks. So you will get to see what are what other things people apply on top of the vanilla GANs that we showed. So GANs, because they are like adversarial. So an example being this. So we all kind of what was the main idea behind GANs, that I have a training data, like a maybe a collection of images. Okay, just one second. What happened there? Yeah, okay, yeah. Yeah. So what is the main idea behind GANs? That I have a collection of images, right? And so they come from they come from a certain distribution, right? Some P of X, right? But now if we want to generate more images from this distribution, right? So if we had access to this original data distribution, we could have just sampled from that distribution and we could have generated new images, right? So at the end of the day, what do we want with GANs? We want to generate new images. So that is what we essentially needed. So in an ideal case, we would have access to the true data distribution and we would have sampled from that distribution, and that would have given us very good images. However, the problem that we have at our hand is we only have some limited number of training data available accessible to us. So maybe some a few thousands or even a few millions are only available to us. So from these few images that are available, right, so from here you cannot predict or cannot have any idea about the distribution of the data, right? So you do not still know the true distribution of the data. All you have access to is some samples from the distribution, right? So the entire philosophy of GAN is that how can I learn an approximate distribution that will be close enough to the data distribution, such that this approximate distribution I'll use to sample, and I'll get back new images, right? So this is actually the story behind the entire neural network, that we are trying to approximate some functions. So here, in case of GANs, we are trying to approximate the data distribution, right? So and just to give a recap of what is happening, so we have two parts in a GAN: the discriminator and the generator. The generator, the job of the generator is to take a random sample from a Gaussian, which is this random input, or the Z vector as we denote in vanilla GANs. And the Z vector is taken as input by the generator, and the generator, based on this random vector, generate some image in the image plane, in the image space, basically, right? And these images, we sample these images from the generator side, and the true images are also sampled, and the discriminator's task is basically to discriminate between the real and the fake images. By fake, I mean the generated images, right? So as long as the discriminator is able to tell what is the real image and what is the generated image, that means that the generated images are not as good quality as we would like, or they are not as realistic, or they are not as similar to the given samples as we would like it to be. So finally, we want the generator. So basically, this leads to a game between the discriminator and the generator, where the generator is going on trying to generate better and better images, whereas the discriminator's task is to catch which are the fake images, right? So in the end, since we want the model to generate good quality realistic images, we want the generator to win. And by winning, what do we mean? We mean that the generator should be able to uh, generate images in such a way that the discriminator now no longer can separate out these two, right? Your generated and real images are so similar to each other that now the discriminator is confused that what is the real one and what is the generated one. So this is the goal behind GANs, right? So this is the goal behind the vanilla GANs, that we want to, through the generator, we want to approximate a data distribution in the absence of the true data distribution, such that the approximate data distribution can be sampled, and we can get good quality images out of them, right? So now, why do we need different GANs? So what is the problem of this particular architecture, or like why is this not enough? So we'll look at some examples and we'll know like what are the levels of complexities that people have put into the like future GAN architectures. I mean, future to the vanilla GANs. So then you'll get an idea that why these complexities are required. And also, one thing to be always remembered is that GAN training is one of the most difficult tasks. So training a GAN is not a trivial task at all. It has a lot of instabilities and so on. So this unstable training of GAN makes it really, really difficult for complicated models to be trained. So you'll find that with each variant of GAN that you see, there'll be a lot of each paper will have a lot of training nitty-gritties associated that we'll see in the next slide. So which will basically help stabilize the training of these models. So all of these papers that we see around us, all of them came into existence because of some necessity, right? So because the existing GAN models were not able to handle some subtle things. So one important thing out of that was the complexity of the images. So for example, if you look at this male image, this image has different levels of complexity. So if you just forget about the face part, you can see a human outline with a green shirt, right? Then if you look a little bit more closely, you'll see that there are 2 ears. A little bit more closely, you'll probably see that this guy is smiling and so on. So what I mean to say here is that images are inherently very hierarchical in nature, right? So there are a lot of levels of complexity in a single image. So some features are like very easy to detect. They are what we call as coarse features. Coarse features means, suppose when you see a painter draw a portrait, the painter generally just draws, the first step that the painter takes is to draw the shape of the face and maybe the shape of the body, and just give some very coarse colors and so on. And as the painting progresses, the painter starts looking at the like painting the eyes, painting the facial features and so on. And then even at towards the end, absolutely at the end, when the painting is almost done, the painter actually, if you see, they adjust the colors, right? So maybe a little tone of some yellow color here, some skin color there, and so on, right? So this is how images can be organized. So they go from coarse level to fine level features. I'm extremely sorry about the noise that you are getting in the background. So there's some festival going on. So just bear with me. Anyway, so yeah. So the point is that, so this hierarchy of features that you see, the coarse to fine grained, so we need, it has been shown that this vanilla architecture is not actually handling these things separately, right? So all it is taught to do, all it is learning to do is that you give a random vector as input and it will generate the entire image, and you are just trying to compare the real images with the fake ones on the discriminator. However, in things like progress GAN, so this is one of the variants that we wanted to touch upon, and it has already been touched upon by Sir in the classes. So the point here is that I'll try to model all these different levels of coarseness, right? So initially, you can imagine this as, like I said, in the first step. So this one that you see, it's completely blurred. You do not cannot make out anything out of it. However, if you look at it a little bit closely, you'll understand based on the skin color and the dark colors here that maybe there's a human out there, maybe there's a human outline out here somewhere. Then you go from this very, very coarse feature to a finer feature. So now you can see maybe the hair color distinctly, some sort of a dress color, and maybe the ears forming. And you do this, you go on doing this, you start increasing the resolution, and at the end, when your resolution is maximum, you arrive at some image some picture or image which is like very very detailed on every level. So now you can make out all the fine grained features that are embedded in the human face, right? So the progress GAN people, and also maybe subsequently many other GANs, they took up this approach of hierarchically modeling these different levels of features, right? So in order for the GAN model to understand these different these small subtle points. Yeah, okay. Yeah. So, just to give a background, we just touched upon how GANs, what is the story behind GANs, and also now we are slowly progressing towards some of the variants of GANs, and what are the requirements, or what are the necessities, what necessities led to the like authors to come up with these architectures. So one thing in this is, so we are going through this progress GAN where we are seeing that the model here is actually trying to look at the different layers of features that a human face, or the different scenarios that we see around us have. So there are multiple generators and discriminators here, not only a single one. So a normal GAN would be maybe somewhat like this, the last one. Here instead, there are multiple levels, right? In the first level generator is only trained to generate 4 cross 4 images, right? And even the discriminator, on the discriminator side, what you do is you take the real images, convert them to 4 cross 4 by some downsampling method, and compare the generated versus the discriminated images, right? So this part takes care of the extremely coarse level features, right? And then what you do is, in the next step, you take this 4 cross 4, and so this is, you can understand that this is a network which takes the latent and then generates. So you upsample it, you go on upsampling that latent until you reach a 4 cross 4 dimensional matrix, right? And now the GAN's job is to make this matrix meaningful such that it contains some details of the image, right? Now, in the second step, what you do is you go up the hierarchy by a little bit. Okay, so you do it in powers of 2, right? So you had started with 4 cross 4, so now you are going into 8 cross 8, right? So again, what happens is, so here, what we do is, we, instead of just having a direct network from the latent to the 8 cross 8, we have this 4 cross 4, and we are just adding a fresh component to the generator model, right? So basically, you have this latent, you convert it to 4 cross 4, that is again converted to 8 cross 8 by upsampling, right? In the same way, in the discriminator also the same thing happens. And now you have a generated image with dimension 8 cross 8, a real image with dimension 8 cross 8, which you have already pre-computed from beforehand. And now you are comparing these two by the discriminator. So all of these, like the quality of the generated images will be very very dependent on how well the discriminator is able to separate the reals from the generated ones. So as long as the discriminator is confused, we are on the right track. So similarly, as we process, you can see that there's an arrow here. So initially we do this. Once this is trained, then we do this, and we go on doing this until we reach here, right? So 8 cross 8 becomes 16 cross 16, then 32 cross 32, 64 cross 64, until we have a proper 1024 dimensional image, right? So this part is what we generally look at. So this is what we know, right? So yeah. So now we generate our generator is able to generate a 1024 cross 1024 image. As the training progresses, this is the last step. And the real image is also 1024 cross 1024. I mean, it's converted to that size, and then you are able to basically distinguish between the two, right? So this is, so these two networks are actually just the same, just that the generator upsamples and the discriminator probably is downsampling and so on. So good, so you can have a, like, I would say that these methods that we show, it's okay to go through the slides and what sir has taught, but also, I mean, a good amount of understanding can develop by looking at the individual papers as well, because we are just covering um maybe the high level overview of the paper, but what goes on inside is so much more complicated. So what do we achieve by this? So first we are, so you can see that with this x-axis, this is the progress of the training, like I said. So you are now, you first learn to basically learn the course level. Did something happen? Okay. Okay, sure. Nothing. Yeah. So yeah. So as the training progresses, so first you are learning the course level features. The generator is learning to model the extremely course level features, probably which are not even clear to the humans. Then in the next step, it learns some more, maybe a little bit more finer level features, and then it continues until it learns the very, very fine level features, right? So initially, if you suppose use a vanilla GAN or the GANs that were there before Progress GAN came, you'll see a lot of blurriness and the coarser, the finer details were not there, and so on. So those problems were eliminated by this GAN, right? So this is one very well-known variant of the vanilla GANs that we see. So you can see that it's nothing but the normal GAN only, just that we are doing it hierarchically. Hence the name progress, because it changes, or it basically depends on how the training progresses. Okay, so now one detail about this is like, how do we convert? So suppose we have a 16 cross, we have started with 16 cross 16, and in the next step we want to convert it to 32 cross 32, right? So how do we do that? So that is basically these people, something happened. um okay. Nothing is there. Okay. So the point here is that how do you go from the 16 cross 16 to the 32 cross 32 output, right? So here, by output, what do I mean? You started from a latent, here you got a 4 cross 4 output. Here you started from a latent, you got a 4 cross 4 output, then an 8 cross 8 output from the 4 cross 4 output, and so on. Here also this happens, like from 4 cross 4 output, you're getting an 8 cross 8, 16 cross 16, and so on, until you are getting a 1024 cross 1024 output. But now the 8 cross 8 output that you are getting, exactly how you are generating that also has a little bit of detail. So like I said, that individually each of these papers, they apply a lot of methodologies, which may be very problem dependent or very, very architecture dependent. So what these guys do here is they have given an example of how to go from 16 cross 16 to 32 cross 32, right? So they take the 16 cross 16 image, right? And then so so basically what they do is, using this method from the 16 cross 16, they take the 32 cross 32 output by upsampling, right? Converts it to RGB, and then they also take the 16 cross 16, apply some nearest neighbor interpolation of the 16 cross 16 layers output, and that is, you get a 32 cross 32 once again through this nearest neighbor interpolation, and this 32 cross 32 is added with the already available upsampled 32 cross 32, right? And you are adding, so you're converting both of these to RGBs, and then you are adding them through a convex combination. So this is very similar to what we saw in ResNets. So in ResNets, remember that in order to do away with the vanishing gradient problem, we were using a skip connection, right? From the previous layer, we were directly sending um, like the feature maps information to the next layer, so that like, because yeah, just to make sure that the gradients are not vanishing. So the concept is very similar here. So there's an arrow here that you can see. which basically makes sure that this nearest neighbor interpolation is added to the output of the 32 cross 32 image also. So I think the idea behind this is that the courser and this entire computation, so you can maybe go through the paper, but one idea is to like apply some smoothness in the sense that you add the coarser, so 16 cross 16 is supposed to be coarser than the 32 cross 32, so you are adding this coarser to the finer, and that leads to some smoothness in the generated images, but in the output 32 cross 32 image. So however, more details of this you can like look into um, once we are done with this session, and you can go back at the paper and have a look at it. So here, instead of like plainly blindly adding the two branches, like what happens in ResNet, here we are having a like a weight of alpha and 1 minus alpha, right? So 1 minus alpha we are adding to the this branch, and one the alpha we are adding to this branch. So this is how, and the same thing happens on the generator side, sorry, discriminator side. However, because we are going from lower dimension to, sorry, higher dimension to lower, we are basically doing the opposite thing. So here we are upsampling, here we'll downsample, right? So it's the same thing, just that one has upsampling and one has downsampling, because in the discriminator, what we are trying to do is we are trying to go from the image space to a single neuron, or maybe some binary prediction where we are predicting zero, I mean real or fake. That's why we want to go from a very low resolution, very high resolution, to a very low resolution, and that's why this downsampling thing happens. So the generator and discriminator are like the opposite of each other in terms of the architecture. Okay. Right. So again, like you'll find in every GAN paper that they have some contributions of their own, right? So some contributions were given by this paper also. So again, most of these were introduced to ensure stable training of the GANs. So this architecture that you are seeing, it, while we look at it, it appears to be very simple to train and all. So there's only a progressive training of different architectures here, different hierarchical architectures here, but actually it is not so. The training actually is not very simple. So uh, at that time, researchers used to take up a lot of steps to make sure that all these so the training was as stable as possible. So the first thing that they introduced was mini batch standard deviation. So as it says here, sorry, the standard deviation for each feature in each spatial location of over a mini batch is computed and averaged. So it's the mini batch standard deviation that is getting computed, and that is concatenated to all spatial locations at a later layer of discriminator, right? So you are basically taking the standard deviation with respect to each feature over a mini batch, right? So you are adding some mini batch information, mini batch related information to some later layer in the discriminator, and that has been shown to help a lot, right? So this is one of their contributions that they have introduced in this paper, that the standard deviation of each feature in each spatial location is first computed over the entire mini batch, and then uh, averaged, and this is concatenated to all spatial locations at a later layer of discriminator, right? So this is one like contribution that they are making. The second one is more intuitive in the sense that so they are trying to ensure that, so this equalized learning rate, so what they're trying to ensure here is that um, whenever, so if you think of the backprop algorithm, so what does backprop do? It calculates the gradient of the loss with respect to the to all the weights that are there, to all the trainable weights, and then once the gradients are available, the new weight values are updated based on the learning rate, right? So however, different layers of the, or different parts of the neural network, the weights that are there in the different parts of the neural network, that may have, because of the scale, because of their values, the gradient values might be different for the different parts, right? So what happens because of that is, with these different so with these different weights, different gradients that you are getting for the different weights, when you update them using the same learning rate, the updates become like different for the different layers or different weights, right? So which again leads to unstable training. So here what they want to do is kind of indirectly equalize the learning rate for learning for all the weight vectors or for all the weight matrices. How they are doing it is that you have a some you at the some for some wi weight, right? There's a per layer normalization constant. So for each layer there's a normalization constant that is given by c. So I'll divide this wi by c, right? So what this does is exactly what it says here, that I'll try to keep the weights at similar scale during training, right? So if all my weights are automatically scaled similarly, right? If the scales are similar for all the weight matrices or weight vectors throughout all the layers that I have, then no matter what my learning rate is, the gradient updates will be pretty similar, right? And if the gradient updates are very similar, your learning is actually very stable during for all the layers, right? So again, these are all maybe these are specific to this paper, but suppose in future if you come across a um, like a problem statement and you're seeing that your model is not working because of different levels of learning in different layers, these are some ideas that you can borrow from these papers that we are going through, right? So you can just try to make sure that all the learning in all the layers is very similar through this normalization of the weight vectors, and then that will basically solve your problem. So the idea here is not to mug up what these people are doing. Rather, it's good to know these things, that okay, these things in an unstable training environment, these things work. Maybe all of them do not have very good intuition, but these things have been shown to work, right? This mini batch standard deviation equalized learning rate. So you have to yourself think of so whenever you come across a problem statement and face similar problems as these guys have faced, you can borrow their the contributions that they have made, the ideas they had, and you can apply it on your own problem. So yeah, that's the main point we wanted to convey here. And also the third contribution that these guys had was pixel wise feature vector normalization in generator G. Again, all these names are kind of like very intuitive, and they kind of give away everything that these guys wanted to do, right? So pixel wise feature vector normalization, so basically what that means is normalize the feature vector in each pixel of G after each convolution layer, right? So in other words, what they do is, suppose I have n feature maps, okay, and I am at some location x comma y, right? So I take what I'll do is I have this. So this is an activation map, right? So this, as it says, that axy is the original feature vector in pixel x comma y. So I'll take this a of x comma y, which means that I'll take the activation map at location x comma y, and I'll divide it by this quantity. What is this quantity? So I'll take so this is n is basically the number of channels, you can think of it like that. So I'll take all the values of all the feature maps at x comma y location for across all the channels, right? So that is given by this j. So xy is the pixel location, j is the channel, right? I'll take all the values from all the feature maps at pixel location xy across the channels, and I'll compute this. I'll basically compute their sum, compute the sum of their squares, right? And to avoid computational overflow, we are adding an epsilon, and we are doing a square root of that. So it's like dividing by some sort of variance, right? So, and this is how you normalize, right? So this is your final uh, activation map is given by this b of x comma y. So you converted this a of x comma y to b of x comma y. So all these steps, the three steps that you see here, all of them came into existence just to ensure smooth training of the GAN, right? So and all of these ideas can be used pretty well in other further research as well, right? So so this is how the pixel wise vector normalization happens in generator G. Just note this thing, that this pixel level normalization is only meant for generator, so it's not done in the discriminator, right? Okay. So, if we want to look at some examples, so the examples can be looked at here. So these are again taken from the examples are from the slides only, but again you can go back to the paper and have a better look at some of the better examples. So you can see that in many cases, some the semantics, by semantics I mean that you can see this image, for example, the bed is not really lying on the floor. So some of these images, I mean, they do not make too much sense. You can understand that the model was trying to create kind of a bedroom. So there's some white patch which looks like a bed, and there's some wall and other things around. However, the model could not do a very good job. So this was an older model. Similarly, you can look at this also. So similar problems are there with all these. That either they were blurry or they were not semantically meaningful. There were distortions, noises, and so on. However, if you look at their generations, not only are they higher resolution than the previous models, they are semantically sound, I mean, comparatively compared to these two. And the resolution is also good, the blurriness is not there, and so on. So in that way, we can attribute maybe the improvement that we are seeing here, those can be attributed to this hierarchical formulation, that you are going from, you're trying to model the uh, you're trying to model the course level features first, then the final level, until you reach the very fine level features. So that is what is helping them create these high resolution, very realistic images. Okay. So this is about progress GAN. So the main thing to be remembered is this, how they are trying to the main concept of this hierarchical training, and also these three contributions that they are making, right? So for more details, again, the paper itself is very good to, it's very beautiful and easy to read. So yeah, I mean, people are encouraged to go through it. And yeah, the examples also look good. So yeah, I mean, one thing can be obviously agreed upon, that this is still an older paper. So a lot of progress has happened in the world after this, and especially now GANs are becoming outdated themselves. So they have been replaced by diffusion models and so on, but we'll not touch upon them at this point. But yeah, you are welcome to read them on your own. But yeah, I mean, GAN research on GAN is becoming a little bit obsolete, because the entire GANs have been overtaken by diffusion models now. And diffusion models, the good thing about them is that they are more stable in training. However, their feature spaces are not as semantic. So what do I mean by feature spaces are not as semantic? We'll go to the next section, and we'll have a look at what is called as the style GAN, right? So here we'll get an idea of what we mean by the semantic space, etc. So this is again another variant which is pretty different from actually the regular GAN that you saw, the vanilla GAN, as well as the progress GAN. Even the progress GAN has many of the parts similar to normal GANs. So, style GAN came into existence because of a certain reason, right? So, for example, so as it's written here, that one problem that used to be there with many GANs was the limited control of specific features, right? So, if you go back to this first image, you'll see that okay, I have a list of once the training is over, all we have access to is the generator, right? So I'm like sampling from the Gaussian distribution, some multidimensional Gaussian. Okay, yeah. Yeah. The idea is that I'm sampling from a multi-distributional Gaussian, and that Gaussian, and I'm passing that random vector through a generator, and that generator is giving me an image. However, I have no control over the image anymore, right? So it's only like from the Gaussian, whatever the Gaussian returns, the generator is like trained to predict an image or create an image based on that. Here, as a human or as a user, I do not have any function, or I do not have any control over the generations, right? So suppose, so a lot of works came. Suppose an example being like, if you take maybe this image, right? So you can see that the woman has a certain hairstyle. Now maybe I want to convert her black hair into blonde hair, right? So if I want to do that, and change this specific the hair attribute of this person, um, it was seen that while you are able to do it through the GANs that we saw till now, the face would completely change, right? In order to change one feature of the person, the entire person would be changed, all the features would be changed, right? So then people started thinking that what if we have access to, we do something so that we only have so while we maybe we want to change one attribute or two attributes, we have control over all other attributes, or in other words, that it is, we will decide what attributes we want to change, not the Gaussian anymore, right? So that is where style guns came into existence, right? So what it tries to do is, it automatically learns unsupervised separation of high level attributes, stochastic variation, and scale specific control attributes. So even though, I mean, this looks a little bit difficult, but the main thing is that I want to have as much control over each of the, I mean, each of the attributes of an image as possible. So the attributes again can be, so borrowing idea from the previous GAN architecture that we saw, the attributes can be coarse level attributes, middle level attributes, or fine level attributes, right? So course level attributes may include just the pose. So which way is your face looking at in the image, the general hairstyle, face shape, etc. So these coarse level features, middle level features like finer facial features, actual like very fine grained hairstyle, right? So I can, my general hairstyle as a woman can be long hair, and then there might be different haircuts for a woman with long hair, which are different for different people. So that can be a middle level, middle resolution feature, eyes open, closed, etc. So it's the same concept that you can see, that course level features are like low resolution images, so which look at maybe very, very coarse things, like the examples given here. Middle will be somewhere in the middle where you're looking at finer things, and very fine resolution is the one with the highest resolution. So I think I gave the example in the beginning that when a painter also paints, they start from the coarse level feature, then go to the middle, and finally maybe once the painting is almost coming to an end, you'll see the painter adding different colors, adjusting small color variations. Maybe the eyes, they want to make a little bit more blue or something like that. So these different color based variations, etc., micro features and all, they are controlled at a higher resolution. Okay, so these features are basically the what we want to convey here is that these features are present in these resolutions. So coarse is present in a smaller, middle is present in the middle, and fine is present in a larger resolution, right? So what we want to do is, we want to control all these attributes, right? So we do not want the model to like just take a Gaussian distribution, sample from it, and just generate something out of the blue. What we want is, if I want to have a woman's image to have a specific hairstyle, that woman, I mean, the woman should remain same. Or maybe we want to add mustache to Shah Rukh Khan's image. So Shah Rukh Khan should not change. Maybe just the mustache is added to his face. So that is what we want through StyleGAN, right? And so the first thing that they did was, so I'm like repeating every time that in the initial phase of the GANs, the like there's too much dependent on the random vector, right? So if you have too much dependence on the random vector, what does that tell you? That um, you are so why is this problematic, or why is this limiting? Because you have a Gaussian of distribution of maybe 512 dimensional Gaussian, and now the Gaussian is going to return some vector to you. So it's not you, or it's not like the model that has any control over it. Right? So you have this random vector, and this is what you were sending to the generator before. However, now they are saying that we'll not use this vector directly anymore. Rather, we'll learn from it. Okay, we'll encode this input vector into an intermediate vector to control different features. Right? So once you learn this, so then the learned vector can be used to can learn a lot of things. First of all, it can carry many vital information, and then it can be used to control the specific features of a face, or of a scene. Right? So how does it do it? So first, this random vector is taken and normalized, and then there are 8 fully connected layers. So you can see all of these 8 fully connected layers are here. So this is called the mapping network. And at the output, you are getting a 512 dimensional W vector. So this is what we call the Z vector, and this is the W vector. The W vector again is of the same dimension. So this was 512 cross 1. This is also 512 cross 1. This W vector is what you are sending to the generator for further processing, right? So this is the main one of the main like contributions of StyleGAN, that is moving on from completely uncontrolled initial vector to a controlled initial vector. So here now you are giving the model an opportunity to learn some vital information instead of just giving pure noise to the generator, right? So this learning enables the control that we are talking about. Okay, so now, yeah, so what happens then? So again, to start with, we had a latent code, we are normalizing it, and we are like having 8 FC layers, and we are finding this W vector, right? So now how do we process this? How do we utilize this W vector? The processing is actually pretty similar to what we saw for progress scans. Okay, so progress scans were also like 4 cross 4, 8 cross 8 cross 8, 16 cross 16, and so on. So this is also very similar. Okay, so how they utilize this W vector is not as straightforward as in normal generators. So in normal generators, you take the noise vector and you upsample it until you reach the image space. Here it's not as simple. There's a bit more math goes into this. So the idea is still the same, that I'll go about it in a hierarchical way, but how we combine this W vector is something that we can see here, right? So the first thing that happens is this. So you have this W vector. There are two things that are happening. Suppose you have a conv layer, right? This conv layer is giving you some output with some n number of channels, right? Now, the first step that you take is you normalize the channel by its mean and variance, right? So if xi is this like conv output at a certain channel, what you do is something like this, the one that I'm marking. So you take this xi minus mu of xi, which is the mean of xi, divided by sigma of xi. So you are normalizing the channel by its mean and variance. That is the first step that you do, right? Second step that you do is you take the W vector and you learn an affine transformation from that W vector. Okay, and that affine transformation is given by A. So you can see that A's are there everywhere. So it's the same shared parameter. So you have the W and you have a A, which is again learnable. So you learn the affine transformation from W, and what you want at the output is something which is of dimension 2 cross n, right? So why 2 cross n? Because n, again, remember, n is the number of channels. So we want 2 because we want to learn two things out of it. Okay, so one thing is called this ys comma I, one thing is called this yb comma I. S comma I is basically some sort of scale, and b comma I is basically some sort of bias, right? So now what is this ADA in step? In the ADA in step, what you do is so you have this xi and these y's, okay? So you have normalized it here, xi minus mu divided by sigma. This part we already talked about. Now this scaling factor you are multiplying, right? So yeah, so this scaling factor you are basically multiplying, right? This ys comma I and the yb comma I you are adding. So that is called the add-in operation, right? So finally, what do we get here? We had this 4 cross 4 here. Now we computed this. Suppose we do a step of upsampling, then we have an add-in. Add-in operation is exactly this one, right? Then we suppose use a conv layer, right? And then we do this normalization, and then again we repeat this add-in step, and this gives you your 8 cross 8. Okay, so yeah, so this is what is going on in a single layer, right? So this is a pretty complicated like formulation, right? So basically what it does is it transfers the W. So whatever W learns, okay, uh, from the mapping network to the generated image. So whatever W is capturing, that is basically transferred to the generated image. Now module, and the second step says what module is added to each resolution level of synthetic network, defines the visual expression of features in that level, right? So basically it's very similar to what we were doing in progress scan also, that at every level we are trying to learn, features that are like connected to that level, right? So this 4 cross 4 would mean the coarsest features, then finer, and so on until you reach the very very fine grained features at 1024 cross 1024. So it has been so shown that moving away a little bit digression from what we have been talking about. So this W vector that we are seeing, this 512 cross 1 dimensional vector that we are seeing, so this is not because we are learning it. So previously it was just a Gaussian vector, the Z that we were using. Now we have a W which we are learning, right? And you'll find a tremendous number of papers which analyze this W. It has been seen that this single vector is able to, yeah, this single vector is able to encode a lot of detail uh, about different like hierarchies of or different details of an image. So let's take human faces for an example. So this W vector is so semantically meaningful that if you do a control, so suppose you are a point in the W space, and now if you move in a controlled way from that point, you can make a person smile, the image of a person smile. You can add maybe hair to the at the top of the head. You can change the hairstyle. You can add eyeglasses and so on. So basically, this W is a very very semantically meaningful, rich vector space which carries a lot of information, and all those information are uh, like stored in that space in a very very specific manner, right? So a lot of research has been going on, at least till the diffusion models came and beat the GANs. So till then a lot of research was going on in how to manipulate this W space to like generate many variations of images, how to make sure that the identity is not changed at all when you are maybe changing parts of an image and so on. And also now following this research, even in the diffusion models, even though you don't know about it, even diffusion models do have something very similar to this. Maybe not in terms of architecture but a feature space. So instead of W there's something called an H. So H is there. In the diffusion models, and people are now trying to identify what are the meaningful features in the diffusion in that H space. So yeah, so this is about style GAN. So when once you go to the paper, you'll see a lot of examples of how you are transferring the style of one person to another. So if I'm suppose wearing glasses and I have a friend who is not wearing glasses, so I can transfer my eyeglass or my style of smiling to that friend's uh, that friend's face basically. So that is a pretty amazing thing to do. And so yeah, I mean, you are encouraged to go through the style gun paper, and there are other variants of style gun like style gun plus plus, style gun 2, style gun 3, and so on. So all of this you can have a look at and just try to find out like what are the differences between this architecture and style gun 2's architecture, for example. So those can be good exercises for you to look at to understand more what is happening, and develop an intuition behind the models. So, wanted to touch upon this other GAN architecture called cycle GAN. So, I'll not talk about it in great detail, but a little bit of just to touch upon like what it does, right? So, cycle GAN has this unique capability where suppose I have this input image where you can see that there's a background and there's a horse roaming around, right? So now instead of the horse, I want a zebra image, right? So what I'll do is I'll not take a separate zebra, right? So what I want is that in this image, this horse should be replaced by the zebra, right? But I do not have a, just understand that I do not have a training set like this, right? Where wherever the horse is, exactly at those pixels the zebra is located, placed. So I do not have anything in the training set like this, but I still want to transfer this style of the horse to the zebra such that the resulting predicted image will be very similar to this one, right? And this horse will get replaced by a zebra. I may have other zebra images which are like maybe in some other shape, other like height, etc. But this is what I want at the end of the day, that given my input image, I want to transfer this input images style to another image where this horse has been transformed to a zebra, right? So there are losses like cycle consistency loss and so on. So maybe again these are very important tools. And just to clarify, or just to inform that the losses that people came up in GAN papers, like the cycle consistency loss and so on, they have been like applied in like many other domains outside GANs or generative framework. So the cycle consistency loss that is there in cycle GAN, so that has been applied in many other papers that have nothing to do with GANs. So it's a good idea to actually go through these loss functions and just keep them in mind, so that in future if you are into research or something, you can apply them and you can get pretty good results. And the other variant that is already there, and I'm sure a lot of you are aware of it now, because that has created kind of a major hype in the AI world, is text to image models, right? So I think in the RNN classes, we already touched upon image captioning, right? So image captioning is what you are given an image and the model has to come up with an English language description of that image. That is called image captioning. So then 2 to 3 years back, people started thinking of, okay, let's reverse this direction. So now I'll give a piece of text to the model, and the model now has to imagine what the what the resulting image is going to look like, right? An advantage of that is that if you want to suppose, if the model now learns a mapping between text and image, suppose now I have a like maybe the example that we were giving, so this image, so I want to change the hair color to blonde color, right? So I can just give a textual instruction to the model that change the hair color of this woman's image to blonde or something like that, and the model will do it for me, because we do not know a better way to, I mean, it's the like talking or writing is the easiest way of communication. So if we are able to give this text to some model which can imagine what the text is describing in the form of an image, then we can control many other aspects of the image which we were not being able to control in the normal case. So text to image models are the flag bearers of that. So instead in this formulation, instead of giving only noise as input to the generator, we are conditioning it. We are conditioning it through the textual description, right? So this text is first transformed into an embedding, concatenated with the noise vector, and then given as input to the generator. Right now, the model's task is the formulation is actually pretty similar, that you still have a GAN, but now you are conditioning it based on the text. Now the model has to learn that based on this text, what can the image look like. So this, for example, this flower has a lot of small round pink petals. So this is the prompt. We are calling these textual descriptions prompt these days. So we are giving this as the prompt to the model, and the model is generating this, right? So for a bit of context, so now so this would be a relevant work maybe 2 3 years ago. Now we have, many of us have probably heard of works like Stable Diffusion, DALI, Mid Journey, and there are many other models which given a piece of text, they can generate wonderful images. So all of them, again, the only difference is that this part is replaced with diffusion models. So again, like all of these, whatever we went through today, they are like different research problems for you to go through, and yeah, I mean they are very interesting applications of the deep learning architectures. So yeah, so like slide wise, this is what I had today, and we'll quickly. I think I have found some progress scan repo for you to look at. So I kind of like, even I need to go through that by myself. So let's see if we can understand it well. So okay, this is something else. Yeah, we'll open it in Colab. So these will be shared with you. So yeah. Okay, so this is the progressive GAN that we were talking about. So yeah, if I yeah, right. So what are the important factors in progressive GANs? So one is this equalized learning rate, one is pixel norm, and a convolution block. Okay. So some few things to remember: that equalized learning rate, what were we trying to do here? We were trying to train the model with almost equal updates. So we cannot have different learning rate for different layers. Instead, we try to make sure that the weight scales are similar across different layers, such that when you apply the same learning rate on top of it, the updates are very similar. So all the layers of your neural network are learning similarly to a similar scale, right? Pixel norm is where we were looking at the pixels, and we were normalizing across channels, normalizing the activation maps across channels, right? And so this is yeah, so these are the factors that we are going to put in. Your resolution goes from 1 to, it first stays as it is, then it goes to half of what it was, then 1/4, 1/8, 1/16, and 1/30, 32nd, and so on. So there's a lot of code here, but we'll first go through the pixel norm part, because this you can easily identify, right? So okay, yeah, so what is the pixel norm code doing here? So yeah, I'll just mark it. Yeah, so again, if we go back to what we had here, yeah, so we can see one thing, that the pixel norm, right? So what it does is, it does this kind of a thing. So it takes the feature vector, feature map, activation map, and then it does this normalization. So this math it does, and we'll see that the code base is exactly doing that. So okay, where are we? Too many things open. Yeah, here. Okay, so likewise, we had an epsilon, remember, in order to reduce computational underflow, right? And then now we have an X of shape, batch size, cross channels, cross H, cross W. Again, channels is coming before batch size, because sorry, before H and W, because in PyTorch it is like that. right? So, and this part is what is calculating this. So you can see, oops, you can see this is the x represents your activation map. So you remember there was a square root on the outside, right? And then there was a square on the inside. So x square dimension equal to 1 means it's doing it channel wise, right? So this entire thing you can very well recognize, right? So this is the exact same thing that we did here. This exact same formulation that we saw here. So here epsilon is taken to be 10 to the power minus 8, whereas here, yeah, it's again the same. This is the sign for 10 to the power minus 8. So this is the code for the pixel wise normalization, right? So now we'll go back to this WS con 2D, right? So this is some sort of a convolution layer, right, where there is some sort of normalization that is going on, right? So let's ignore that for now, right? So here in the conv block, what they're doing is self.conv1 equal to that conv2d that we are defining above, right? Self.conv2 also is some that variation, again, that same variation of convolution. We are then initializing the leaky ReLU. So in GANs, generally one norm is to use the leaky ReLU instead of the actual ReLU. So I hope you remember that why we are using the leaky ReLU is because uh, in ReLUs the negative parts are made to be zero. To avoid that, the leaky ReLU is used, which deviates from the zero a little bit in the negative side, right? And PN is this pixel norm class, right? So remember one thing that we talked about is, again going back to the slides, is that this pixel wise feature vector normalization happens only in generator G. So going by that, so you are first passing your X or image through conv1, then this leaky part. So this is adding the nonlinearity, and then this pixel norm part if it's on the generator side, otherwise not, right? Otherwise it's X. Then again you are doing the same thing for conv2, and then again passing through this pixel norm, and then you are returning X. Right, so this conv block, as it says, will be used for both generator and discriminator, but inside pixel norm is used only in generator, like I said. So some warnings are already given here, which will be useful for you to understand, right? So, and also, like I said, every GAN paper comes with its own nitty-gritty. So here it's like the order they have mentioned is very specific, that you first have to do conv 2D, then the activation, and then the norm, right? So it's not conv 2D, then norm, then activation. This order also is very important, right? So then we'll move on to the generator part. So the generator, we know it does what? It is basically uh, like it starts with 4 cross 4, then 8 cross 8, and 16 cross 16, and so on. So that is what is like described here, right? So in this part of the code, right? And also the more interesting part that I wanted to touch upon, especially in the generator code, is that also it's there on the discriminator side also, is that you if you remember, we were again looking at the this part where we were seeing that the addition or the like upscaling of the 16 cross 16 to 32 cross 32 is not straightforward. So there's a resonate like connection which is going from here to here, and then there's a convex combination that is happening. So similarly we see the same things here. So first there's a interpolate, oops, yeah, first there's an interpolate, right? So with a scale factor of 2, right? And then your RGB layers is basically converting both the like both the upscaled image and the output image, right? Output of the upsampling that you are doing through neural network. So both of them are converted to RGB layers, and then you are sending it to this particular function, which does what? It does an alpha of generated plus 1 minus alpha of upscaled, right? So in the generated, yeah, so these two, final upscaled and final outer, what are going into this function, and then the alpha is the input, and this part is the output. So the idea is that whatever we have put in the slides, all of these can be traced back to the different parts of the different architectures that you use. So here you can see that the mini batch standard deviation part is also here, right? This is on the discriminator side. So the discriminator also has a similar architecture, just that maybe some parts of the generator have some, like for example, the pixel norm is only applied to the generator. Similarly, the uh, mini batch STD, that is only applied to the discriminator, which you can have a look at, right? So again, everything in the generator is about upsampling, and everything in the discriminator is about downsampling. But the main concept still remains the same: how you combine, how you like convert a, 32 cross 32 image to a 16 cross 16 image is very similar to the opposite, how you convert 16 cross 16 to 32 cross 32, right? So these are the two main the generator and the discriminator block. So there are a lot of details. So maybe even you do not need to go into all of this, because all of these are like already coded up in PyTorch. So this is only for our understanding that what is written in the slides, whether it is matching with the uh, you know the code or not. And this convolution layer that we saw in the top, that is what is probably helping us with the equalized learning rate part. So yeah, I mean, maybe this one I'll have to take a look at again. I'm getting a little bit yeah. So it's written here already that it's the equalized learning rate on the contour layers. So this is probably provided by the program paper only. So again, let's go back just to see what is happening. So yeah, equalized learning rate is given by this. So you have a WI and you are dividing that by C. However, very often it used to happen that whatever whatever you kind of whatever is there in the paper on code, it's a little bit different. So it doesn't look as simple as just dividing weights by a simple C. So yeah, maybe it would be good to look at on your own. So yeah, so these are the main parts. So one is this equalized learning rate part, this one, right? So then this pixel norm part, this we already could decode. The con block, right? So which is built up of these WS con D layers that we saw above, and only invoke pixel norm if you are on the generator side. The generator side is again made of these sequential layers, pixel norms, then con transpose and leaky relus, right? As expected, because con transpose, because you are upsampling this time, right? And this is the uh, these are the like different blocks of the the progressive GAN, and yeah, this part mainly encodes what happens when you okay, somewhere else, yeah, this part encodes what happens when you are trying to convert the uh, 16 cross 16 image to a 32 cross 32. So you are adding the interpolated image and so on. So all of these, I mean, I think they'll become much more clearer if you go on and play with the code and maybe print out a little bit of what is there in the model. If you print the model, and if you suppose look at the what is there in these individual maybe lists and arrays that they have created, so that will be much more helpful. So yeah. So then they have given a testing code as well. So you can just do it to find whether your model was successfully created or not. So this is not a training code. This basically was given to you to give a feel of what is going on internally, right? So even I opened up this, oops, yeah, so this is the progress scan paper basically, right? So it is an NVIDIA paper. So you can go through all of this. So uh, see, the data set is available already, and the trained networks can also be found in some drive link. So yeah, so this is again another thing that you can have a look at. So some interpolation, some other results are given in the YouTube already. So all of these images that we went through, they are already explained in great detail in the paper with explanations on all of this, the equalized learning rate and so on. So the name of the paper is Progressive Growing of GANs for Improved Quality, Stability and Variation. So it would be, I think, a good exercise to have a look at it. So yeah, where are we? Okay, here. Yeah, I think that is what I had for this week. So um, yeah, so this is the second last class. So we'll have another class next week, Tuesday. And yeah, that will be the end. Hope you had a good session. Okay, so if nobody has any questions, then maybe we can close it. Okay.